Hello, my name is Julian Smith and I'm from Force Fusion. Tonight we'll tell you a bit about how we made our robot for the year of 2020 for the FIRST Robotics Competition. We'll give you a view in what we do, particularly with LabVIEW for our robot, because all of our code, well, almost all of it, is made in LabVIEW. I'm going to give you a bit of an introduction about us and the team as a whole. Explanation about the robot and the game. I'll tell you about our build season, which is 6 weeks long, so very short. We'll talk a bit about the FRC extension, the autonomous program, the telehelp program, and as a little bit of a bonus, we used our robot this year in a VREE competition as well, and we'll tell a bit about this as well. So, the introduction. We are Force Fusion of 2020 and 2021. Every year we have a new team with extra students and high schoolers who will build a new robot. Our old members will either go on to be board or will be mentors or don't go on with us. As you can imagine, we are always a new team, so every year we rotate people. And thus we are very much beginners. So we'll give you some examples about our code. Don't laugh too much at us. Yeah. So a little bit of the introduction about our board members. These people are the ones who guide us most and help us with the mechanical part of the robot, electrical and the software part. Jona is one of our board members as well. And next year, the three of us, including a few other people, will take it over for the new team. Some fun facts about the team. As you can see, we're from a lot of countries, mostly from Russia and Europe, and a few of us are from Asia. Our students are a nice mix between boys and girls, so we have 8 girls and 15 boys. Fun fact is the total travel of the team equals to 7 times the distance around the world. And we have a little bit of a overview about our support members. So mentors, we have 14 of those, board members are 5, and then we have 2 leading. The students average out at about 18 years old, so we're all very young. The mentors about 21s, as well as the board members, and then we have the lead, which is a bit older, but that's one of our teachers as well, so that's why it's 39. Here's a list of our partners. Over the years, we're now 4 years old. We have accumulated quite some partners. We're very proud of these, and but are always looking for more. Because making a robot is of course not cheap, and everything, well, we get it from our partners. About FIRST. FIRST is a big organization in America. It stands for Inspiration and Recognition of Science and Technology. They try to inspire the upcoming youth in the fields of STEM and make them enthusiastic about everything about engineering and what comes with it. We firmly believe in this model as well, and which is why we also try to take our students and our high schoolers in the process of building the robot. So that's about FIRST. FIRST makes a game every year. Every year also a new game with new gaming elements, and thus we always make a new robot which will be completely different from the one before us, from the year before. This year it was a bit different because of Corona. Of course, we couldn't go there, so they made the game changers at home challenges. This meant that from home we could send in videos from our robot playing the games we were asked to do. The at home challenges were based on the game of last year. So this was the field we had with the render. It was from 2020. We have a robot for that as well, but this year we got the at-home field, which was basically a blueprint of how to make your own field. With this field we made different courses. So we had 5 games in total. In these games, one of these games was AutoNav and another one was Hyperdrive. This was basically the driving of the robot. So in AutoNav we had to make an autonomous program and where we make the parkour. And with the Teleop was a manual operated system where one of our high schoolers operated the robot. I'm very proud to say this year we placed 107th of the world total with Hyperdrive. We also have our interstellar accuracy game, which is the right top. And here we had to score points from different distances, and by doing so we could accumulate more points. Next to that we also have a game where we had to look where the balls were, the power cells, which we had to collect for the games. And yeah, the robot had to decide which path it should walk by seeing the balls. These are a few fun pictures about our game field. You can see we have a lot of fun with our team where we deep in the night make our things. So yeah, then it brings us to build season. Build season starts the first weekend of January, in which we get the where we get the game changers, so we know what the game is going to be, how it's going to look, and we get the manual. After the first weekend of January, we have 6 weeks in total to make our robot. And yeah, it's a really short time, but every year we have succeeded to this far, so we try our best. So the top left, you see the game changes, the logo, and at the bottom right you can see something we use for our build season when we just start up. We first always start with a strategy, so we know what the game is and how we are going to play it actually. And for this we also of course need to decide on what parts we are going to use in the robot, what is going to be our best strategy, and how is the design going to look. We made an app for this, our students, and basically if we put our parts in here, our ideas, it will give out a stepwise plan of how things are going to look. Here we have a few other pictures. In the top you can see one of our high schoolers designing the robot in SolidWorks, and the other pictures are about the assembly, which was, I think, somewhere around 3 in the morning when this happened. These are some of our modules. So the robot, which you can look after our presentation when we go into the break, is made out of our drivetrain, our storage, which is in the middle, our shooter, electrical box, which we try to keep as small as possible this year, and our intake. Or maybe a fun fact about the robot as well is it's one of our smallest and most lightweight robots we have ever produced. Also one of our fastest robots. So every year we actually try to innovate and become better. This is a fun video of our software practice. Yes. So yeah, this was the very beginning where we started out programming our drivetrain and autonomous driving. Here you can see how we are, I think, 4 in the morning trying to get the PID working. Yeah, it is a really tedious process sometimes as real beginners to get something as basic as a PID working. So for the ones who cannot see the robot right now, this is the robot of 2021. It's named Cutie, and we're very proud of it. This is one of our games we played, and so one of the videos we sent to FIRST to be judged. Let's see if this time it does work. So you can see via intake, we take the balls in and they go into the storage to be filled up through the shooter. The way we designed it can be a continuous process, just loading balls and directly shooting. Also something we made this year was a autonomous aiming process, so we didn't have to bother all that much with adjusting the robots and yeah, well, create and shoot. Okay, which brings us to our next part of the presentation, which will be given by Jona about the FRC extension.
Yeah, so before we go actually into the code that we, at least these beautiful people, wrote this year, I want to explain a little bit more about the LabVIEW extension that we get from FRC or from FIRST, because it's a little bit different than the normal standard LabVIEW that we have. First, I want to talk a little bit about the project, the WPI library, which is the actual library that we get from FIRST. Something about the actuators, the sensors, and then the many different VIs that exist in the project. And this is the actually getting started screen, a bit different than the normal one. So in the project we automatically get these VIs. There are actually only a couple of them that we are allowed to edit, because some of them are actually mandatory for FIRST to keep the same for safety reasons, so they can always control our robot when it's actually on the game field, so we don't do crazy stuff with it. The main ones that we can actually edit are autonomous independent, begin VI, finish VI, and the tally up one, which I'm going to talk a little bit about later on. The first is the actually WPI library. We can do, we get an extension which is quite large and has so many extra things in it. We can control the robot via joystick, so just your normal joystick that you get from any console. But we can also actuate motors, get inputs, outputs, have communication via PWM or CAN bus, and we also have our launchpad, which is our central control unit, which we actually also can communicate to. Then the actuators. This is Falcon 500, which was one of the central motors that we had this year on the robot. As you can see, there are many different types of motors and controllers that we can have on the robot, but this one was special in particular because we can have all different types of closed loops, open loops, PID systems already in there, current control, limit switches, and everything in there. So we can control every aspect of the motor, which is kind of awesome for us to do. For sensors, we can also control different types of sensors. Your normal gyroscopes, encoders, potentiometers, normal switches, but also your standard analog or digital input sensors. Then we come to the begin VI, which kind of looks like this, where we have a reference which we always have to call to. And this is kind of the VI where we declare all motors, sensors, encoders, everything. It's always set up like this. As you can see on the top, the one motor drive left and right is specifically for the drivetrain, where we can control 4 motors at the same time. And the rest are just sensors and other motors. When we come to the autonomous VI, this is always the first 15 or 30 seconds that we have during a match, where we can select different type of autonomous programs via the structure. And on the left, you already can see again that we have to declare all the motors again. So the actual RoboRio knows, okay, we want to move these types of actuators, or we want to look at these type of sensors when actually operating the robot. And then we come to tally up. It looks a bit clustered and a bit fake, but this is just where we can actually operate our robot with our joysticks, and this will take about 2 minutes, and then the game is done, and you have to score as many points as possible. It looks like it's not looping or in general, but that comes because the main VI actually has a while loop where the tally up is actually always looping around, so we can continuously control the robot. And you can also see the other different types of VIs, the begin VI and the autonomous VI in particular. And FIRST actually controls this part. So they can say, okay, we're now doing autonomous, and then after the actual 15 seconds they control the robot saying, okay, now you can actually go to tally up. Instead of us doing all the controls and programming it ourselves, this is a lot easier. And the last thing is the dashboard, which I already briefly explained. This is our control center where we can see all our inputs, outputs, see how much voltage is left in the battery, if we actually have good communication or not, and on the right you can see some of the controls we have as well. So we can also read and write other stuff that actually we want to see from the robot at any time, at any moment during the match. And I think we're going to autonomous.
Thank you, Jonna.
Yeah.
Hello everyone, my name is Ansali Panjaitan. I was a programmer of the autonomous routine for Force Fusion this season. And this year I'm also part of the board members. I'm the chairperson of Force Fusion this year. And I'm going to tell you some things about the autonomous program within LabVIEW for our robots. And first off, I'm going to focus on the autonomous driving, because that's basically the most important part, let's say, of the whole autonomous. And yeah, for autonomous driving, we want the robot to drive as accurately, as precisely as possible. And for that, we always use a PID controller. And maybe most of you already know what PID controller is, but maybe to shortly sum up, it's basically for the robot to travel an exact distance based on the set point that we give. So as you can see, this is the graph of one of our PID movements, and one of the line is the graph of the left wheel, and one of the other is the right wheel. This is just driving straight. Yeah. And what we're proud of this year is basically because we are able to step up with our PID. Now we have something that is called motion profile, and we are doing this motion profile within MATLAB first. So what we do is we actually simulate the path that we are going to use, or the path that we are going to drive in MATLAB, and then we transfer it to LabVIEW. So as you can see in the left side, you might remember this picture. This is one of the path of the game that we have to drive. And on the right side is one of the movement in that path that we simulated in MATLAB. The MATLAB code itself is a result of an internship of our former member. So I'm not going too deep into the MATLAB code itself. But what MATLAB basically does is it divides this path into 100 different steps. And for each step, the simulation is going to determine how much distance the right and left wheel should travel in order to complete that step. And the simulation also determines the turning angle on each step, which we also call the turning factor. Next on, this is the things that we can actually change within the MATLAB code. So we already made the MATLAB code adjustable and according to our dimension. So the dimension of the robot, also the dimension of the field. But what we can do when simulating is basically we input the starting point of our path, also the ending point. And we also input two other points in between to determine how the curve will look like. And after that, the simulation data is written in a CSV file. And this CSV file is then copied into the RoboRio directory, which we can then read out from LabVIEW afterwards. This is the CSV reading inside LabVIEW. As you can see, we can extract 6 values from 5, I'm sorry, I cannot count. Yeah, we have 5 values that we can extract from the CSV file. The top one, our encoder, is basically the distance that needs to be traveled by the right wheel for each step. So later on when this looping, it's going to give 100 different values. The same thing for L encoder, that's the left side of the wheel. R plus L encoder, oh sorry for the typo, is the addition of the two. We have also turning factor, that's the angle that I mentioned to you before. And the total length is a constant number actually, that's the absolute total distance that the robot needs to travel during the 100 steps. And what we can do with these values exactly. So yeah, these values are basically used as an input to our PID controllers. And this whole mess is our block of PID controller. Apology for the mess and what we call spaghetti code. But yeah, as you know, we're students, we're still learning, and this can definitely be made better. But yeah, we have several different things going on here. On the bottom left, we have the reading and the resetting of encoder, where we actually gain or extract the feedback from outside world. So what's the real distance traveled from by the robot? And then we have the CSV file, as I mentioned before, up there. We also have two kinds of PID here. And why do we have two? Because normally we only drive straight or turn in our own axis. But with motion profile, we want to be able to make a curve, which means we have to travel straight while also making angles. And that's why we have two PIDs. The first one is connected with the outputs of CSV file, the distance, and that is used to control how much distance the robot wants to travel. And the second PID block here is used to control the turning angle. So maybe another thing to add is because our robot is mechanically unable to drive straight because of some friction, more friction in one side. That is also why if we only want to drive straight, we need this second PID to be able to control that such that the angle is always 0 and it drives straight. So that's about the PID. And this is where we output the values to the motor. So the actual voltage is applied as the input to these blocks. Yeah. Beside the PID for motion profile, we also have two other kinds of PID. The more basic ones, to only drive straight or only to turn, which can be selected in the case structure before. And yeah, even though it's messy inside the PID blocks, we can hide it outside. So this is actually the PID VI we have connected. Yeah. 4 of PID VIs, that means we're driving 4 paths. And as you can see, up there is the input of the directory of our CSV file, which we're reading from. And the integer input is the selector of PID program. So here 0, it selects for the motion profile PID. So yeah, that's for the driving of the robot autonomously. And this is a demo of, not really a demo, this is one of our tests of motion profile using our old robot, because back then we didn't have our robot yet. This is, I think, 3 or 4 paths combined into one continuous loop. Yes. That was for autonomous driving. But of course, we also want other functions such as detecting balls, intaking the balls, or storage, shooter, all those kind of stuff, sensor readings. And of course, because it's autonomous, we always have to think of sequence. So following flowchart and stuff like that. And that is why this sequence structure is one of the most used blocks in our autonomous program. And as you can see, in sequence 1, here we have our PID block. Here we are extending our intake, which is a pneumatic thing, so it's a piston. And then we are zeroing the outputs of our intake and storage motor, because we don't want it yet to turn on. And then in sequence 2, we drive, and we turn on the motors of our intake and storage because we want to be ready to take the balls. Next, we actually already get to the ball, and that is why we extract the intake again back to its original position. And it's looping in a while loop because once the ball is detected, which I will show you the code later on. But once the ball is detected, then it goes out of the while loop, it goes to the next sequence, and do the same things, drive, and etc. until it reaches the final point. Yeah, of course, maybe as Yona have mentioned before, we have vegan VI, which declares all the components we have. And outside of the sequence structure, we have to call this component first. So here we're calling the motors to our drivetrain, the intake piston, shooter piston, intake wheels, the storage motors. And next is an example code of how we read the sensors. Here we are calling the sensors from the vegan VI. And then here, as I mentioned before, we read out the sensor. And here we're actually detecting the falling edge of the sensor. Okay, the code that I showed you before is for one of our game called Galactic Search. And what we have to do is basically shown in this video. It has to detect the balls and collect the balls. So I'm just gonna play it.
3, 2, 1, go.
It still goes quite slow, but yeah, it's not bad. Yeah, maybe you can hear the motor stalls a little bit there. But yeah, that is basically for autonomous program. And I'm going to hand this to Matthijs that will explain about the TeleOp program.
Hello, I'm Matthijs, I'm the TeleOp guy, and I'm going to try and explain you something about the TeleOp program, or part of the program. So to start off, maybe a little recap, what is TeleOp? It's actually quite the opposite of autonomous. It is the control of the robot with a controller by a human player. So it's located right here in the main VI, but before I am actually going into the TeleOp VI, I would like to explain something about this chunk right here. What is it? Why do we have it? Well, what like mentioned before, we want our robot to actually autonomously aim when a button is pressed or something. So actually we don't have to do it ourselves. So first we thought like, yes, we have the limelight, we can actually aim it, but then we found out that my laptop is empty. Sucks. So I need to go through it really quickly, I assume. No. No, we needed also a distance measurement, and the limelight is an estimation, and it really sucked because now we could not properly estimate where the robot needed to shoot. So we bought a LiDAR. The LiDAR, what does it do? It actually measures the distance with light, but then we encountered a problem. We programmed in real time, and the RoboRio could not handle the speed with which it needed to read the LiDAR. It could only read milliseconds, and we needed microseconds. So we were stuck. We didn't know what the hell we needed to do. So we went to one of our sponsors, VREE Technologies, and they messed around a little. They said like, hey, we can program directly on the FPGAs, which made it possible to actually read the values of the LiDAR, and so we could read the distance to properly aim. Now, into TeleOp. This is the TeleOp program, so just let's directly get into it. Where do we get our inputs from? That's from right here. We actually call up to the values of the controller from the begin VI that's connected to the USB port. And from there we get the values and disperse them to two arrays. So the top array right here is for the digital inputs, and the bottom one right here is for the analog inputs. So now we have put all those values from the controller into arrays, but now we need to know what values are where in the array. There are two ways of doing this. We can put numbers in front of here, and we can predetermine the locations of what buttons goes where. Or we can just keep checking what is where, and because we've been using the same controller for 4 years, that was the best options. So now we know a little what values come from where, so we just need to spread them out over the certain functions like activating the wheels or turning the turntable. These are quite simple, I won't explain these. But these two, I really want to explain a little bit more about these. So just directly going into it, the vertical aiming. This right here is the VI for the vertical aiming, and that's what this part is for, that I just explained. It actually measures the distance. And from here, the anti-right number, it teleports to here. And from here, we have the values and we map them to actual distance. So what we did, we put our robot on the field, and we said, all right, so what angle do we need to actually hit this goal? Then we entered it, we put them a little back, and we all entered all these values into a graph, and like that we have made autonomous aiming. So moving on, what is this? Well, we had the linear servos, and they should have a reach from 0 to 180, but they don't. We don't know why, but they go from 27 to 120, we found out, so we just made a limit on it, so it cannot actually break itself, and it goes to the servo. Yeah, right here, what's this part? We have some mechanical and electrical setbacks. So when we are shooting, the robot actually starts to shake, which means the values the LiDAR is getting will change. So it will start to adjust itself, which will make the shots really inaccurate. So we decided, alright, so when the shooter wheels are turning, we just say stop adjusting, so we can minimize the offset we get. And we can just turn it off completely, so we don't use it. Let's say we're doing a game where we need to drive really fast, it's annoying to keep having the servo extend and retract and extend and retract, so we just say no, stop. Now moving on, this is the horizontal aiming, it's also automatically. So what is happening in this mess? Starting off here, we have the turntable encoder, and now we have it go through a case structure with the turntable sensor. So this is, when it reaches this point, we say, alright, we reset the encoders, so it knows where it is again. It's actually like a home function. Then moving on right here, we actually convert the encoder values to degrees, and right after here we make sure it cannot turn further than 180 degrees or minus 180 degrees, so it won't break itself. Now looking at this part here, it actually gets the values from the limelight, because we still use the limelight for horizontal aiming. It gives us how many targets we see and the offset angle of the center of the vision to the center of the target. So all these values go to here. What happens here? Well, we say, alright, what do we say? Yes. Here, if we see more than 0 targets, we will get the values from the PID. Else it will just stop, or else we will just keep rotating, really annoying, we don't want that. But here, we have, if the offset is bigger than 0, it will actually get the values from the tolerance. So tolerance is how far it's away from its actual target. And if it has reached the target, the difference is 0, and it will just give you a value of 1, and the goal is 1, so it will just also stop turning. Oh yes, it actually worked really good at start. We have a reflective tape right here, and we'll just follow it. And the plan was that we could just drive along, and yeah, it will always aim at the target. Well, moving on, now it will actually get into the core, I call it, the center, so the intake, the storage, the shooter. It looks like this. I've tried to clean it up a little. What I've done, I've put all the inputs on the left side, all the outputs on the right side to make it a little bit organized. But now let's get into these 3 VIs. What are these 3 VIs? Well, so like I said, I just started going at it with no knowledge whatsoever, so I just started with, I need to pick up balls, so extend the intake. Now I need to get the balls further in, and then I have the shooter, like the balls go up, and now they need to go to the belts of the shooter. How do I do that, and when do I know that? So I started making all these things, but then I realized, like mechanical and electrical and pneumatics were like, yes, we're going to make this robot really small. They were really enthusiastic about a small robot, and then the software came, and I'm like, shit. So what happens is you get the first ball. The first ball we can just put into the shooter, that's not that hard, we just keep the belts turning. Then the second ball comes, and you would say like, let's just put them as far as possible into the storage. But then the third ball comes, and it is still on the same belt. So what happens is you push the ball up against the balls in the shooter, and that breaks the balls, dislocates the belts in it. So what I did was, I put the ball all the way at the front, I stopped them there. And I was like, yes, now I have enough time when the next ball comes to actually put it all the way to the top and have a pretty nice organized storage. But now it's all the way in the front, so now the ball that comes in bounces off, because it's that close. So I was like, shit, once again, what do I do now? I was like, alright, I'm going to play a little bit with the speeds of the belt. So what I did, first of course, it needs to go to the top as fast as possible. We just want to have the ball gone. Second one, I just put at the front, like there, it stays neat. So what I then do, we have the intake wheels that are on the intake. and just, ooh. I'll just have them turn really slowly, and the belts on the inside really fast. So what happens is that the final ball arrives, the sensor sees it, and it just really softly ejects the ball into the storage, and the storage just throws the ball up, and that way I try to get a little bit of an organized storage without breaking the balls and the rest of the robot. Don't judge me. Yes, so this is the part where we store the ball, so we extend the intake, we see if the intake is out. Here I'm just messing around with plus, minus, is, and to actually manage all those speeds. And I was like, yes, I made this. Now, we also need to shoot the balls. But this VI needs to know what happened in the last VI, so it needs to communicate. So I tried to do something with that too. Yes, I tried. So the student went, so I tried to communicate all these values. I managed, but it appears when I was making this, I was like, yes, there are professional people here, so I need to clean it up a little. It appears I did the same twice. Really nice. And then finally I have this part, and it's actually in the middle because I communicated all the values and I was like, I have some values left. So I made this one to actually communicate the last few values in between all these VIs. Yeah, feedback is welcome. So moving on to the very last part, after that we can go to the fun stuff of VR. We have the driving. Now, we have multiple ways of driving because we have some high school students, because we aren't allowed to drive, it sucks, but they are. So we need to, do what they want. So they say, how do you want to drive? Like, do you want flippy drive, do you want tank drive? And there's all kind of different ways of driving, so we made them right here. So for example, we have the controller values and we just put them into the array. Oh, here I can show you with 3 and a 2. So what normally would be value 3 and value 2, we put them on the first two. In this case, these are the flippies. And we put them, it's called arcade, but we're using the flippy drive, and we put these values to the motors. Now moving on, these are all our ways of driving. And it was everything I had to tell you, so Jona will take over.
Thanks. So, in the beginning of September last year, we got an invitation from another company called VREE to collaborate on an actual other project where we were able to use UDP and VR to actually move a robot. So this is the robot that we used. This is the one I actually worked on 2 years ago. So we joined X Prize, and we actually did part of the challenge where we had to bring human presence into an environment where you actually don't want humans to be. So we worked with other companies, and what the general idea of the, or at least the mindset that we had, is that we used the free SDK, so from the other company, and in that way we could move the robot, while the other person is also moving actually in real life, and also be able to grab balls from the ground. With also actually feeling the difference between the actual hardness of the balls with the gloves that we have. What the actual idea behind this was actually to get some kind of bomb clearing robot, so you could actually feel the different types of bombs that were on the ground, some that were armed, some that were not armed, and in this way the robot could actually pick up the bombs instead of actual people doing it. So these were the companies involved. Us, of course, VREE, which helped us extensively with the VR, Hubram with more about the communication, and Sensegloves with the actual haptic feedback gloves. This is the free SDK, which VREE actually gave us to use. This is kind of the environment where we actually get all the information from. So every little bit of information that we get is from here. And these are the suits and the Sensegloves, which Matthijs is wearing very nicely. It actually has many types of different sensors all over your body, and it can track every movement that you make, from waving your hand for actually stepping. And then you have the Sensegloves, which are actually haptic feedback gloves. Then one of the most fun things that you could do is actually squeeze an egg and you could feel it pop in your hands. Then we actually go into the code. We used a UDP connection to the robot, which it has a router. That's how the communication works. So what we do is we broadcast a simple connection, which the server will pick up and it will actually also broadcast the same message back to us, and you can see the actual UDP broadcast VI in there as well. When this pinging has been done, we actually have a stable connection and we can actually get data from the server. For receiving the suit information, we first want to confirm that the actual information coming from the server is the actual one that we want, which we use these blocks for. The first block that you see on the left is just that we can just read a part of the string that we get from the actual server and confirming that we actually have the information that we want. Then we come into getting the usable values. This one is specifically for the hips, but we have to endian swap them because the numbers are around and we get different values than we actually want. And from here on we can actually use the values and start moving. And as you can see, we have many different types of values that we want to use. Hips, arms, legs, everything that is necessary, and as long as we don't receive information, we just feed back the last stated information that was given by the server, so the robot doesn't just jump around and go back to its 0 point because it got a 0. Yes, so this kind of looks the same as what Ansley showed you. This is the actual PID block, which we also use because it's fully autonomous. On the right there is the actual VI that I just showed you. It's actually just the connection and we get all the values from there, which go directly to the PID block, so when I'm making a step, the robot will automatically follow. And one of the things was that we wanted to actually control the arms on the robot. So the second I put my hands as high as my shoulders, also the arms will raise up and stay in that position. This way we could also control the storage, but because in the second the arm is down, the storage will also start working, which is, oh yeah, well, that's the PID, which I already explained. But yeah, this is the storage. It kind of resembles the one Matthijs also showed you already. And it kind of works in the same premise, but instead of having one storage, our robot was special because we had two, because we wanted to shoot two balls at the same time. But it just works in the premise that we just see the sensor and then it stops. And so we also know, also the VR knows, okay, the robot is full. Don't start taking balls anymore. Yeah, so this was our first driver test where we just set to the SDK move 1 meter, and this was also with second year's robot. As you can see, it works fine until the end where it just started going a little bit too far, right here. So we stopped it before it actually would run into someone. So this is a video of the actual working code, which we also applied for the X Prize.
For the ANA Avatar X Prize, we are creating a completely wireless system that allows users to control their avatar intuitively using their body. Our initial prototype consists of a caterpillar robot with a grabber that can be steered via human interaction. We are using Etten motion capture technology often used in the entertainment industry, prototype haptic VR gloves, proprietary low latency networking software, and a robot platform developed by our generation Y and Z team. With our design, we are creating a robot that moves around freely, aware of its surroundings, and capable of distinguishing specific materials in its environment. Due to the unfortunate global COVID-19 pandemic, our preparations of more than a year for the FIRST Robotics Competition were cancelled. Therefore, our ingenious robot was looking for a new purpose. The FreeSense team asked us to cooperate on.
Cut shortly because there was more, but it was more about other things. Yeah, this is kind of it, what we used VR for. No, not again. Okay.
This is a message from FIRST
For centuries,
about this year.
sports have played an integral part of our culture. Moving, collaborating, competing, celebrating. We rally around our athletes, lift them up, and admire their awe-inspiring moments and stories that give us hope. The nature of traditional sports is shifting, and we have the power to be forces for change and redefine the game. No matter whether our talents lie on the court, in the lab, or with the controller in hand, there is an athlete inside each and every one of us. And let's work together to champion every sport and every person that plays the game. It's time for us to revolutionize the way we play and move. It's time to be game changers.
So Game Changers was the game of this year, and it's something we always try to do, innovate and inspire the next, which is why I really want to show you this video. This was our presentation. I hope you liked it a bit. Because we had only an hour, we had to skip over a lot of stuff, so please do also ask us in the break or if you still have time left about the robots. We could go on for hours, of course, so do come. This is our motto: inspire them and let them amaze you. Yeah, I hope you enjoyed.
And don't forget to follow us on social media.
So that was amazing. I really, really liked that. And of course, we saw your code. You don't know the general accepted software development practices, but you still got an amazing result because you got it working. So that's I think. How long did you develop on this?
So basically, we started in the beginning of the school year, where we have 6 months of preparation, where we get the students to think about how to code a robot and whatever we can use for our robots, not only software-wise, but also mechanically-wise, what they can do, and electrical-wise. It's just a whole preparation process. The actual development of a robot starts when, in the first weekend of January, when we actually know what the game is going to be and so how the robot needs to look. After that, we have only 6 weeks to actually go from absolutely zero actually to our end results, which we have here right now.
It's amazing. Yeah, it's really cool. And which were the biggest problems that you had during the software development? Was it debugging? Was it getting the code to work? Was it figuring out which functions to use?
Well, oftentimes it was communication-wise. We make use of the VREE, which is one of the products and main process from NI Technologies of NI, of course. But it's become a bit older, and because probably also some mistakes in our code, we have sometimes trouble in shooting our code into the VREE and failure to operate it actually.
That's not only in the RoboView. So does somebody else have a question? The audience. Right?
Yeah, one question. Do you spend full time on this, or do you also study next to it?
Next to it, we of course also have school, so it's actually altogether 6 weeks where we basically have 1 to 2 hours of sleep every night, and also go to school and build a robot. It's
amazing.
Yeah.
Amazing. Yeah.